Hi, my AB kids. This is section 10.3, an introduction to that. It's still U-substitution like section 10.2 was, except now you have bounds. It's a definite integral, so there's bounds involved, and if there's bounds involved, then you have to adjust them because you're changing an integral from being in terms of x to being in terms of u. So that's pretty much the overall idea in this section coming up. So it's going to be a lot of the processes that are similar to what you did in the last section, but in the end we're going to have to evaluate them, the integrals, using f of b minus f of a. So here's your intro problems. Number one, I have to choose what my u is going to be, and for this one you usually take whatever's inside the parentheses, so we're going to let u be 1 plus x to the fourth, and I'm going to take the derivative of that. Du would be 0 plus 4x cubed with respect to x dx. And then I look at the original integral and I see I have an x cubed and I have a dx. I don't have a 4, so I want this 4 to be out of there. So I'm going to move the 4 to the other side. That means I'm going to divide by 4, or make this 1/4 du is what x cubed dx can be. Alright, then I'm going to look at the bounds. Before I put my substitution together, and you can do these pretty much in any order you want. You could do the bounds first if you'd like, but I usually do them as a second thing. My bounds have to change, and it bases off of what this says right here. I know that u is 1 plus x squared, so I'm going to take my upper bound of 1, and that 1 goes in here for the x, and I want to figure out what the new upper bound is going to be. So u equals 1 plus my upper bound to the 4th power. Well, 1 plus 1 to the 4th is 2. And I'm going to do the same thing for my lower bound. My lower bound is a 0, so 0 gets plugged in here for the x, and it looks like this. 1 plus 0 to the 4th. Well, 0 to the 4th is 0. If I add 1 to it, now I've got 1. And so my new bounds are going between 1 and 2. And then I'm going to set up my integral. I'm going to put the whole thing together. Here's my integral, just like you did in the last section. The lower bound is 1. The upper bound is 2. I have an x cubed dx, which is equivalent to a 1/4 du. And I have a u raised to the 5th power. Now let's put it in the right order so that we can evaluate it. It's still the integral going from 1 to 2. The 1/4 can come out in front like a constant. And I am taking u to the 5th du. So I'm just rearranging the way that that looks. And now let me take the antiderivative. So 1/4 stays 1/4 in the front. U to the 5th would be 1/6 u to the 6. Add a power on, divide by the power, going between 1 and 2. Now I can even make that a little bit nicer by taking the 1/4 and multiplying it by the 1/6. I get 1/24. And that would be then u to the 6th going between 1 and 2. So I'm ready to do my f of b minus f of a. If I do that, I've got the 1/24 in front. F of b is going to be 2 to the 6th. F of a is 1 to the 6th. And 2 to the 6th, if I were to calculate that out, that is 64. So I would have 64. Got things in the way here. 1/24 first. 1/24. And I have 64, 2 to the 6th. 1 to the 6th is 1. If I subtract that, I get 63 24ths, and that is my final answer. And so that is U-substitution for definite integrals. You've got to adjust the bounds so that they fit what the integral is going to be. Now the next one looks kind of complicated because it's got these weird square roots of pi's and such, but it really actually works out relatively nicely. So if I look at this one, number 2, job number 1 is figure out your u, and u is this x squared. So u equals x squared. That means that du equals 2x dx. I have an x, I have a dx, I don't have a 2. 2 comes to the other side. 1/2 du equals x dx. Now, just for fun, some of you might have thought, and I'm going to put it up here, this is not true, so you don't have to, don't write this. Some of you might have thought to take u and let u equal the sine of x squared. which, if that's the case, then du is going to equal, I'd have the derivative of the angle, 2x, the derivative of sine, which is cosine of the same angle, and then dx. But do you see how you don't have a cosine in here? So that's not a good substitution to make. So you're not going to choose to go in that direction. That's why I just took the x squared and not the whole sine of x squared, because there's no cosine here for me to substitute in. That wouldn't work. So this is no good, but this is good. All right, I'm going to take my bounds. Got to adjust them. So my equation is u equals x squared. If I do that, u equals my upper bound of the square root of 2 pi over 3 squared, which actually is kind of nice, right? Because if I square the square root, I get rid of it. So really my upper bound is 2 pi over 3. And if I look at my lower bound, u equals the square root of pi over 4 squared, which gives you pi over 4. And so really they made that kind of nice for you because your bounds now do not have those weird square roots in it with pi's. So let's make our substitution and set up the integral. The integral is going from pi over 4 to 2 pi over 3. I have the sine of u, and I have x dx is equivalent to 1/2 du. And so I'm going to clean it up and put the 1/2 in front. I have still the integral going from pi over 4 to 2 pi over 3 of the sine of u du. All right, so then I've got to figure out, well, what is the integral of sine? And the integral of sine is a negative cosine. So the negative's going to come out with the 1/2. I'm going to put the negative in front with the 1/2 and keep the cosine of u. And that is going to be going between pi over 4 and 2 pi over 3. All right. Now I need to f of b minus f of a this thing, and so I need the unit circle. So you need to remember the unit circle for this. It's going to be a negative 1/2, and then it's going to be the cosine of 2 pi over 3 minus the cosine of pi over 4. And so I go to the unit circle. I've got the negative 1/2 in front. If I go to the coordinate for 2 pi over 3, it's a negative 1/2 and a positive square root of 3 over 2. Cosine is the x value, so it's a negative 1/2. If I go to pi over 4, that's a square root of 2 over 2 and a square root of 2 over 2. For the coordinate, it's the x coordinate, so it's going to be minus the square root of 2 over 2. And so if I put all of this together, distribute it, I guess I can do. Negative 1/2 times negative 1/2 is positive 1/4. And negative 1/2 times negative square root of 2 over 2 gives me a positive square root of 2 over 4. And I guess I can make that just slightly prettier. This is a perfectly valid answer, perfectly wonderful, but slightly prettier would be 1 plus the square root of 2 all over 4. And that's number 2. If I go to number 3 is a square root, and normally whatever's inside the square root is going to be your u, so that's what we're going to do. U is 7 plus 3x. That makes du 0 plus 3 dx. I don't have the 3. I don't even have an x or anything like that, so I'm going to move the 3 to the other side, so just dx is going to equal 1/3 du. And then I'm going for my bounds. My bounds would be u equals 7 plus 3 times my upper bound of 3. Well, that's 7 plus 9 is 16. If I take my lower bound, it's 7 plus 3 times a negative 1. That gives me 7 minus 3, or 4. So they're my new bounds, and I'm ready to set up my integral. So integral goes between 4 and 16. I have the square root of u to the 1/2, and dx is equivalent to 1/3 du. And so I'm going to clean it up, and then I can integrate. 1/3 goes in front. The integral from 4 to 16 of u to the 1/2 du. So when I add a power on, keep the 1/3. If I add a power on, now I'm at u to the 3/2 and divide by 3/2, it's going to turn into 2/3 u to the 3/2. We've seen that kind of stuff before, going between 4 and 16. So I can multiply these together before I even start my f of b minus f of a, and if I multiply them together, now I've got 2/9 u to the 3/2 that I am going to evaluate between 4 and 16. If you remember how these fractional exponents go, the denominator tells you the root and the numerator tells you the power. So if I do my, let me write it out the long way here first. 2/9, I have 16 to the 3/2 power minus 4 to the 3/2 power. Or 2/9. If I take 16 and I take the square root of that, that's 4. If I take 4 and cube it, that gives me 64. This guy's 64. If I take the square root of 4, that's 2. 2 cubed is 8. And so here I am with this. So 64, if I take 64 minus 8, I get 56. So now I've got 2/9 times 56. Gives me a final answer of 112/9. 56 times 2, all over 9. That's number 3. Number 4 is similar. Number 4, I take my u. My u is what's inside the root, 1 plus x. That makes my du be 0 plus dx. And I'm going to come back and talk about that in a minute, because see how I don't have an x dx? I just have a dx? Something's got to give with the x that's here. We're going to play a little game with that. Got to play a little trick. But let's talk bounds first before we get tricky. All right, bounds. My bounds are going to be u equals upper bound of 3. 1 plus 3 is 4. Lower bound is 0. 1 plus 0 is 1. So I've got my new bounds, and I'm sort of ready to take and set up this integral. I'm going from 1 to 4 now. I have the square root of u, so u to the 1/2. I have my dx is equivalent to a du. I'm going to leave a little space. But I also have this x that's kind of lost out there and doesn't have an equivalent. So, like, how do I get that in there? And really the story is, it comes from this guy right here. Can you take this equation and solve it for x so you can make a substitution for what x is? So if I take this and solve it for x, I will get x equals u minus 1. Well, that is what's going to go in to my integral right here. So this is x dx square root of 1 plus x. Tricky, right? A little tricky on that one. So let's see how we can integrate this one. If I distribute the u, this is like u to the first power. If I take 1/2, you add exponents when you're multiplying. So I'm setting up my integral. U to the 1/2 times u to the first is u to the 3/2. I have to add those exponents together. And u to the 1/2 times 1 is just u to the 1/2. Now, all of that I haven't even integrated yet, right? So now I'm getting ready to integrate. If I add a power on, 3/2 plus 2/2 is 5/2, and divide by 5/2, it's going to give me 2/5 u to the 5/2. Add a power on, divide by the power. Same thing with this guy. U to the 1/2, add a power on, that's 3/2. Divided by 3/2 is 2/3. Minus 2/3 u to the 3/2. And that needs to get evaluated going between 1 and 4. This one's going to be a little bit more of a beastly f of b minus f of a situation. So if I plug in a 4, 4 is going to look like this. 2/5 times 4 to the 5/2 power minus 2/3 4 to the 3/2 power. That's f of b. f of a is going to be 2/5 of 1 to the 5/2 power minus 2/3 of 1 to the 3/2 power. That's f of a. F of b minus f of a. Lots of fractions. We love them, right? All right, same thing goes. Square root of 4 is 2. 2 to the 5th is 32. So this is going to be 2/5 times 32 minus 2/3. The square root of 4 is 2. 2 cubed is 8. Now over here with 1, 1 to any power is just 1. So this just turns out to be 2/5 times 1 minus 2/3 times 1. And that one's kind of relatively nice. So let's see what we got. We have 32 times 2 is 64/5. 2 times 18 is 16/3. Then I have a minus 2/5. Don't forget to distribute. Negative negative makes this plus 2/3. And that's what I want to try to add together. So I'm looking at this, and if this were a non-calculator question, you've got to come up with common denominators. And so for this one, the common denominator is 15. Everybody got to have a 15. 64, I need to multiply by 3. 64 times 3 is 192. This one has to get multiplied by 5. 16 times 5 is 80. This one has to get multiplied by 3. This gives me a 6. This gets multiplied by 5, gives me a 10. And so if I were to take all those things and add them up, guess what the total is? 116 over 15. And that is your answer to number 4. All right. That's probably the hardest one right there. Number 5, you've got a cosine squared of theta over 5. You could call it x, you could call it theta, whatever, times a sine of theta over 5. And remember the one that we just did a few minutes ago back in number 2? We chose our u to be just the angle x squared. In this one, see how it has sines and cosines? We want the trig function involved this time. So this time we're going to let our u equal the messier of the trig values. So the messier one is cosine. So u is going to equal the cosine of theta over 5. And that's because in this one we have an extra trig function of sine involved, where back in number 2 we did not. All right, there's my u. Let's go du-ing. If I du this guy, the derivative of cosine is a sine. And it is of the same angle, theta over 5. And then I have to multiply by the derivative of the angle. Well, that would be the 1/5 coefficient that's on it. And that's with respect to x. And so if I'm looking at this guy, I have I have the sine of theta, I've got that piece, I've got the dx, I don't have this 1/5, so I'm going to multiply both sides by 5 to get rid of it. It's going to make me have a 5 du over here. 5 du, and if I were to take that, it's going to equal the sine of theta over 5 with respect to x. So I can now change my bounds. Let's go bounding. So for my bounds, I'm going to have my u is the cosine of my top guy, pi over 5. And my bottom bound is going to be the cosine of 0 over 5. Well, 0 over 5 is just 0, so that's kind of nice. I can figure that out pretty easily. 0 over 5 is 0. Cosine would be the x value at 0, which is a 1. If I go to my handy-dandy calculator, and you can do this, the cosine of pi over 5, you get 0.809. I did that already in the calculator, but you can check me out and make sure that that's correct. So if I take that and put my integral together, do my substitutions, here's how it looks. I have new bounds. My new bounds are upper bound of 0.809, lower bound of 1. I have a u squared, cosine squared, And then the sine of theta over 5 dx is equal to a 5 du, so times a 5 du. And that's what I want to take and clean up here. So I'm going to take that guy, and I want to, by the way, I keep stopping because I keep hesitating. If this was cosine, and I take the derivative of cosine, that's negative sine, isn't it? I keep double checking, double thinking that, but here's what I've got, which makes this be, I can put the negative here, make this a negative 5. So when I pull this out, it's a negative 5 times the integral going from 1 to 0.809 of u to the second du. But there's an issue with that, right? There's an issue because if I take this, do you notice this? Look at my bounds. My bounds are not quite right, are they? I've got the lower bound being on top and the upper bound being on the bottom. So do you remember how we adjust that? We adjust that by taking and flipping them but changing the sign. So this would actually turn into a positive 5 integral of 0.809 on the bottom, 1 on the top, of u squared du. All right, let's go. 5 u cubed over 3, 1/3, going between 0.809 and 1. In other words, I have 5/3 going f of b minus f of a. So that's going to be 1 cubed minus 0.809 cubed. And when I work out the details of that, let's see, handy dandy calculator. If I work out the details of that, I have 1 minus 0.809 cubed. And then that is times 5/3. So times 5 divided by 3. And that gives me an answer of 0.785. 0.785. And that's my final answer for that guy. Whew, 1 to go. 1 to go. Last one. This one, see how I have the trig function, but I don't have cosine with it. So this time when I pick my u, I'm just going to make it x squared. So this is kind of like the one that we did back in number 2. Actually, it's a lot like the one we did in number 2, except my bounds are a little different. All right, so one more try here. I've got u equals just the x squared because I don't have a cosine involved. Du is 2x dx. I have an x, I have a dx. I do not have a 2, so 1/2 of du is an x dx. And so now I'm going for my bounds. U equals the upper bound of the square root of pi over 2 squared, or pi over 2. Lower bound is 0, square root of, I'm sorry, it's not a square root, it's just a regular old 0 squared. 0 squared. 0 squared is 0, and so I can put my integral together. Here it goes. I have bounds going from 0 to pi over 2. And I have a sine of u, and I have x dx is equal to a 1/2 du. And so I'm going to take that guy and I am going to pull the 1/2 out. Gives me an integral of the sine of u du going between 0 and pi over 2. And so if I'm looking for what the antiderivative is, for sine it's going to be negative cosine, makes this a negative 1/2. I'm looking at the cosine of u going between 0 and pi over 2, and I'm ready to f of b minus f of a this thing. So if I do that, I have negative 1/2 on the outside. I have the cosine of pi over 2 minus the cosine of 0. Now this one you should know those coordinates, right? Pi over 2 is 0, 1. Cosine's the x. So negative 1/2 of 0. 0 is the coordinate 1, 0. Cosine's the x. And so if I take negative 1/2 times 0 at 0, negative 1/2 times negative 1 is a positive 1/2, and that is my final answer for number 6. So, as an intro for section 10.3, the whole idea is, same as it was for 10.2, with finding your u and then doing substitutions, except for this one, you needed to be able to change your bounds so you could actually evaluate it and get an answer. So all of these are going to be number answers, not the plus c kind, because plus c's go for indefinite integrals like you did in section 10.2. You can email me any questions. Hope you're all doing well, and I'll talk to you soon. Bye.